all the terms, but we can include only few terms so that we truncate the rest. So that becomes the truncation error. Yeah. And yeah, so we have discussed about that last week. Also, we have discussed about the example problem here. Yeah. Did we finish discuss this one?
Yes, ma'am.
Okay. All right. Thank you. So we finished discussing the example problem. So that now we have Maclaurin series in which we can this is one type, yeah, of Taylor series in which the center of expansion is from xi, which is starting from 0, so that using xi is equals to 0, so that we have the Taylor series now becomes these equations, so that we can apply these equations to any problem that we have. So for example, here we have the exponential of x, so that we can solve the function of e exponential x using the Taylor series, in which here we use Maclaurin series, yeah, so that we put insert the value of xi here is 0, so that we have the value of the function and also the first derivative and so on. So that inserting this value to the Maclaurin series here, so that we have the exponential x will be shown by this series, yeah, the exponential x equal to the Maclaurin series shown here. So that if we draw the curve, yeah, so if we draw the curve here, so that we have the actual solution for the exponential x here, which is shown by the light blue line curve here, light blue curve here. And if, for example, we take only one terms here, so one terms means that we are using zeroth order approximation, so that we have the function here will be shown by the horizontal blue line here. Yeah, so the value will be equals to 1. So we see here that with zeroth order approximation, the error is very, very large. Yeah. And for example, if we further increasing to first order accurate scheme, in which now we use two terms in these equations, so that what we have now is a linear line, so that the exponential x, which is simplified to two terms in the Maclaurin series, so that we have now the curve is represented by the green line here. Yeah, so 1 plus x. So we see now that the curve is already approaching to the actual curve, but still we see the error is quite large. Yeah, so that we can extend further, yeah, to third order, second order, sorry, to second order, so that we have now 3 terms included in the Maclaurin series, so that we have the equation now becomes quadratic equations, so that here we have the equation of 1 plus x plus half squared x. So here we have the red curve here. So this is the approximation. Yeah, it is the second order approximation for the Maclaurin series. So we see here that the error is already decreased. Yeah, so we see there is a difference here. Yeah, approximately near -1 and +1. But for the others, we see that here the value is quite good, approaching to the actual value. And further, if we increase it to third order, fourth order, so we get a curve that is close to the actual solution. Okay, so this is the example of the solution of exponential x with a simplification using Maclaurin series, truncated Maclaurin series. Next, we have another example in which we have sinus x, yeah, curve. So here we have a sinus x curve, so that if we insert the value of the function sinus x, so that we insert the value of xi here is 0, so that we get the value of the function for sinus x that will be equals to 0. And the first derivatives of sinus x will be cosinus x. Yeah, the first derivative of sinus becomes cosinus, and if we insert the value of xi here is equals to 0, so that the first derivatives cos 0 will be 1. And then we have the second derivatives of cos, yeah, so the derivative of cos sinus x will be minus sinus, yeah. So that here, if we insert the value of x is equals to 0, so that we have the second derivatives as 0 is 0 as well. And further, we can extend to third derivatives, yeah, and so on, inserting the value, so that if we write it down, yeah, so if we want to find the value of sinus x, so sinus x will be equals to, yeah, so that will be equals to f0 plus h, yeah, so h is x, yeah, x times the first derivatives at 0, yeah, plus x times squared x over 2 factorial times the second derivatives at 0 plus x to the power of 3 over 3 factorial times the third derivatives at 0 and so on. So if we insert the value here, so that if this is 0, so that will be 0. Yeah, and the first derivative at 0 is 1, so that this is 1. So that we have x here, the value. And then the second derivative is 0 as well, so this will be 0. So that here we have the third derivative is minus 1, so that we have minus x to the power of 3 over 3 factorial plus x to the power of 5 over 5 factorial and so on. So if we see here, if we take one terms in this equations, yeah, if we take one terms only here, so that means we don't have the 0th order. So this is automatically, when we take one terms here, this is automatically first order accurate scheme. Yeah, first order accurate. So using one terms here becomes the first order accurate. And if we use two terms here in the Maclaurin series, we truncate the rest. So this becomes the third order equation. So using two terms in the series, we end up with third order accurate scheme. So this is the result. The red line here representing the actual solution, yeah, the actual result of sinus x, the actual curve. And the linear line here is the first order approximation. Yeah, the first order approximation. So we see here that this is good in the value between -1 to +1, for example, but at other value, the error is very large. And if we extend to the third order accurate scheme, in which we use two terms in the equations, yeah, so that we have third order scheme. So this is the approximation for the curve. Yeah, so we have the blue line with symbol here. And if we use three terms, it means that we have fifth order equations. So we have x to the power of 5. So that's meaning we have fifth order equations to approximate sinus x. Yeah, and we see here that most of the points here is already predicted, approximated correctly. Yeah, but in other position here, for example, from 2 to 3 or more. Yeah, so we see there is a quite discrepancy to the actual result. Yeah, so this is the approximation that we can use. Yeah, and of course, adding more terms, it means that we will reducing the truncation error. Yeah, so that what we have discussed previously is to finding the value of fxi plus 1 from the value of fxi. Now we can also use the Taylor series expansion for another problem in which what we want to find is actually the derivative. So not finding the value of fxi plus 1 as before. Yeah, so before the goal is finding xi plus 1 from the value that we have at fxi and all of the derivatives. Yeah, but now what we want to find is actually finding the derivatives. Yeah, so what we want to find is the derivatives of the function. Yeah, so if, for example, we have the value of fxi, for example, and we want to, we have the value at other position, for example, at fxi plus 1. And for example, we have fxi minus 1 or other at other location as well. So here with this information, we can find the derivatives. Yeah. So we can find the derivatives at xi. Yeah. And why this is important? Because we see that many problems, yeah, has complicated function, complex function in which sometimes it's not easy to find the derivatives. Yeah. So for example, we have these equations. Say we have 2 plus cos 1 plus square root of x, yeah, over divided by the square root of 1 plus 0.5x, and this is multiplied with the exponential of 0.5x. So if, say, we want to find, so that is fx. So if we want to find, for example, df dx, so how can we solve that? So this is not easy, yeah, because we have x as an exponent. On the other hand, we have x under the square root. So this is not easy to find the derivatives. Or other cases, for example, here we have the data from experiments, yeah, in which we have discrete data. Here we have the value from xi1 up to 9, and then we have the function value at those points. So here, for example, we have these data points, and we want to find, for example, the gradient at 1 here. So how to find the derivatives or the gradient here? So in this case, we can use the Taylor series expansion to get the derivatives. So we look again of how we write down the Taylor series. So if, for example, previously we can approximate the value of xi plus 1 based on the value known at xi, so that if we want to find the derivative, so we can do the same way, just for example, finding this value and take the other terms to the left, yeah, for example, so that if we want to find this one, so all of this value should be known. Or if we use the truncated version, so there will be truncation error, yeah. And this, if we do the expansion of the Taylor series forward. We can also expand the Taylor series backward. Yeah, so it means that aside from doing it forward here up to I plus 1, so that we can also use the Taylor series expansion, which is going backward here, for example, to approximate the value at I minus 1. So that if we want to do the expansion backwards, so that we have fx at I minus 1, so that can be approximated by fxi minus, why this is minus? Because it's going back. So the positive direction is to the right, while here we have going backwards, so that we have negative. Yeah, because what we have here will be, so that will be, so this is initially is fxi fxi minus 1, so that will be equals to fxi plus xi minus 1 minus xi, yeah, times the first derivative of xi, plus again xi minus 1 minus xi squared over 2 factorial, the second derivatives, and so on. Yeah, the second derivative of xi and so on. So that if we have this one, because xi minus 1 value is smaller than x minus xi, so that will be equals to minus h, so that we have the value, the sign that is changing with terms. Yeah, so this is positive and then negative h times the first derivative of xi, and then we have this is minus h, yeah, but this is squared, so that becomes positive again, so that will become h, which is squared over 2 factorial times the second derivatives at xi and so on. Yeah, so that we have the intermittent sign from the terms here. Yeah, so that will become negative. Yeah, so positive, negative, and so on. Okay, so this is when we want to do the Taylor series expansion backward. Okay. So that here, if we use the backward scheme, yeah, if we use the backward scheme here and we do truncation, yeah, so we truncate, we take only 2 terms yeah, for example, fxi minus 1, so that will be equals to fxi minus h times the first derivatives at xi, and then the rest here we truncate it. So that becomes the truncation error. Yeah. So then here, if we want to find the first derivative, so we can easily get that one, so that fx, okay, sorry. Yeah, so that if we want to find, if we want to find the derivative, so we can easily do that by move that to the left side. Yeah, so we have, or we can, or say we move that to the left side. So we have fx and xi. Yeah, so that will be here fxi minus, so that one move to the right side. So minus fxi minus 1 over the distance, which is xi minus 1. So that if we see here, so that it means that to find the derivative at xi here, so say we have this function, this is a true function, the actual value, and we have the true derivative. So the true derivative will be the tangent line of the curve. Yes, so this is the tangent line of the curve. So this is the value at xi. And if we have the value at fxi minus 1 here, so then we connect these 2 points with a linear line, so that we have this becomes the gradient. Yeah, so the gradient will be delta y or delta f here, which is fxi minus 1, and this one is h. Yeah, so xi minus 1. So that will be delta f over h. So that will be the first derivatives. And as we seen before that, this is truncated. So actually we have the term here, which is at the order of second h squared, yeah, because this one is h minus h, this one is h squared, and this is truncated. So that if we have this one, yeah, so we can write it down again here. So that actually becomes fxi, yeah, so that will be fxi minus fxi minus 1 over h, yes, because this is a h. So it means that we divide all on the right side with the right side term with h, so that we have 0. The others of square h divided by h, so that becomes 1. So that becomes first order. So if we look at this formula, so this means that this is the equations to get the first derivatives. Yeah, finding the first derivative using backward scheme, which is first order accurate. Yeah. So this is the definition. This is the formula to get the first derivative using backward scheme, which is first order accurate. So that this is the true derivatives, while this one is the approximation with the backward scheme. So we see that there is a difference. Yeah. So we see there's a difference of gradient, of course. So that becomes the error. Okay, so this is the backward scheme as we have seen before. Yeah, so what we truncate is at the order of h square here, but because next it will all divided by h here, so that when it's divided by h, yeah, so this one divided by h, so that we end up with h to the power of 1. So that means the order of the error will be first order. Yeah, first order accurate scheme or first order error. Yeah. Okay, so this is using backward difference. And we can apply this, for example, if we have the data from experiments. Say we have these 5 data, and we want to find the derivatives at x1. Yeah, so we want to find the derivatives here. We have this value. Now, say we want to find the first derivatives, yeah, using backward scheme. So that what we can do is to find the difference of the function value, which is 4.1. Yeah, so that one, approaching using backward scheme. So that we have 4.1 minus 2.3 over 3. minus 1. So that will be 2. Yeah, so that we have the gradient at xi here will be 0.9, in which this is first order accurate scheme. So this is how to find the derivatives. Yeah, so it's quite easy. And we have the second scheme in which this is using the point forward. Yeah, this is using the point forward. So what we do is we connect that point with the point forward or after it. Yeah, so we connect it forward so that if we have this point, we connect with the linear line. So this becomes the approximation while this is the real value. So that using the same Taylor series expansion, which is expanded forward, yeah, so that will have a truncated, this is a truncated version of h squared, so that we can find the derivatives here that will be equals, yeah, that will be approximated by fxi plus 1 minus fxi, so that is the delta f, divided by xi plus 1 minus xi, so that will be h. So that the gradient will be delta f over h. And this will be, because this is divided by h, so that the right here, the second terms here is also divided by h, so that will be divided by h as well, so that we have h to the power of 1. So this is again first order accuracy. So this is how to find the first derivative, ya, turunan pertama, using forward scheme, which is first order accurate. Okay. Now we have a third approach in which now, yeah, we use the point before and after to approximate the derivative at xi here. So we want to find the derivative at xi, in which the true derivative is here, yeah, the tangent line. Now to find this value, so we connect the point before and after. So what we use is not the point itself, but we use other points which is adjacent to it. Yeah. So we have the point as xi minus 1, and we have the point at xi plus 1. So that the gradient here, yeah, the gradient here will be delta f over the distance here will be 2h. Yeah. So the gradient here will be fx and xi, yeah, which is approximated by fxi plus 1, yeah. So this is fxi plus 1 minus fxi minus 1, yeah. Yeah, so that divided by the distance delta x, which is 2h, yeah, because 1h is the distance from xi to I, and also xi minus 1 to xi, and also from xi to xi plus 1. So that the total will be 2h. And this is second order accurate scheme. How come? So that we will see now the explanation based on the Taylor series expansion. Yeah. So say we have previously we have fxi plus 1, yeah. So that will be equals to fxi plus h times fx and xi plus h, which is squared over 2 factorial, the second derivative of xi, plus h to the power of 3 over 3 factorial, yeah, times the third derivative of xi, and so on, yeah. So this is the first equation that we have. Now then we have the expansion, the Taylor series, which is expanded backward, yeah. So we have xi minus 1, which is equals to fxi. Now we have minus h fx and xi, yeah, plus positive squared h over 2 factorial, the second derivative of xi, minus, yeah, h to the power of 3 over 3 factorial, the third derivative at xi plus and so on. So if we want to combine these two equations, yeah, so what we want to find, yeah, what we want to find is the first derivative. So this is what we want to find, yeah, the first derivative. So if we want to find the first derivative, so that we can do subtraction, yeah, so we subtract the second equation from the first equation. So what we have here, so that we can insert the value of fxi plus 1 minus fxi minus 1, so that if this is subtracted, so that will be gone. And then here we have h minus h, so that will becomes 2 times h times the first derivative at xi. And that if this is subtracted, so that it will gone. Yeah. So what we have left here will be plus, yeah, positive, minus, so that will be positive as well. So that will be 2 times h to the power of 3 over 3 factorial times the third derivatives at xi and so on. So if we truncate the rest here, yeah, so we take only one term here, yeah, so that now we can calculate the first derivatives. So that the first derivatives becomes fxi plus 1 minus fxi minus 1, and that is divided by 2h. So all of the terms here will be divided by 2h, so that we have here divided by 2h, and then the truncated terms here will be at the order of 0, h to the power of 3, yeah, then divided by h. So that the resulting here, so that we have at the order of 2. So this means that we have the second order accurate scheme. Yeah. So this becomes second order accuracy. So how can we, what is this formula used to? So this is to find the first derivatives, yeah, using central difference scheme. Central difference scheme, in which this is second order accurate scheme. Okay, so this is the explanation or the derivation of why this method, yeah, we see that the cost of the calculation, yeah, the arithmetic operation that is needed, almost similar to what we have before in the forward and backward scheme. But we see here that using central difference schemes, we have the second order accurate scheme. So it means that the level of accuracy is higher than what we have before. Okay, so that we will return to the slide here. Yeah. So that by using central difference scheme here, now we have, this is the approximated value, and we see that by nature this will approximate the true derivative better compared to the first order scheme. Yeah. Okay, any questions before I continue?
Excuse me, I want to ask something about first derivative, second order, and first order. When I look the figure that show the graph from the first order error and second order error, based on your explanation, before a second order error has more accuracy than first order error, right, ma'am?
Yeah.
And but when I see through the figure, the gap between the true derivative and approximation from the second order error is more larger than first order error, ma'am. So it make me confused about when we said if the second order error is more accurate, why the gap is bigger than this first order.
Okay.
That's what. That's I
All right.
confused.
Yeah, yeah. Okay. So when we talk about the value, yeah, when we talk about the value, say we have the previous figure here. Yeah. So if we talk about the value of the function, for example, sinus x like this one. So the error of this value here is the difference between this value. Yeah. Wait, which one? Yeah, that one. Okay. So this is the actual solution. Yeah. So the distance here is the error. Yeah. If we talk about fx, so the error of fx, the function, the value of the function, so that will be the distance. But when we talk about the gradient, so the gradient will be the slope. Yeah. The slope or the angle. Yeah. So when we talk about the derivative, so that means the tangent line or the angle. So what we see here is comparing the angle, yeah, between all of the scheme that we talk about. Yeah. So for example, we have the first, the this one is the backward scheme. Yeah. For example, we have the backward scheme in which we approximate the slope at this point. Yeah, the slope at this point is by connecting this point and the previous point here. So what we have here, the angle is this one. Yeah. So that this line, yeah, so this is the slope, yeah, which is approximated by the backward scheme, the first order backward scheme, while the true slope is here. So the error now becomes that one. So this is the error. Yeah. So this is when we talk about the first derivatives. And if we have the forward approximation, yeah, if we have the forward approximation, so that we want to approximate the value at xi here by connecting this point with the point before, yeah, with the point before here, so that here with the point after, yeah, because forward, so it means that the point after. So here we have the line here will be the slope, yeah. So here we have the difference between the actual slope and the approximated slope. So this is the error. Yeah. Well, if we see in the central difference scheme, yeah, by connecting the point before and after of that point, so that here we have this approximate derivative. Well, this is a true derivative. So we see here that there is a bit of difference here. Yeah. So we can see here that yeah, perhaps this is not exactly the same. But if we have a parallel line, so that will be, the error will be 0. Yeah, if we have a parallel line. So this is not completely parallel, but you can see here that, yeah, you see that there is a difference, yeah, but the angle is very small. So that the error means that the error is reduced. Yeah. So when we talk about the first derivative, it means that what we see is the angle.
Okay, ma'am. Thank you, ma'am. So I will clarify about this. Also, when we talk about the derivative method, we talk about the gradient, right, ma'am? Not the value.
Yes, yes, correct.
Oh,
yeah,
okay.
we talk about the gradient. Yeah. Yes, that is correct.
Okay, thank you very much, ma'am.
Yeah. Okay. Yeah. So thank you for the question. Yeah. So when we talk about derivative, yeah, this is the gradient. So we talk about the slope, yeah, which shows the gradient. Okay. Any other question? Yeah.
I would like to ask about the, so at first you mentioned about why we need the differentiation by Taylor series. The first reason is when we have function too complicated to differentiate. Is there any example with that problem, ma'am? The function of 2 plus cos 1 plus
Yeah.
root of x. Ma'am.
Okay. So this one, yeah. So this will be your question, Api, yeah. Yeah. So about the first example here, yeah. Yeah. So if, for example, we have this kind of problem, yeah, and we want to find the derivative, so what we can do is that we can just insert the value there. Yeah. So say we want to calculate the derivatives at xi. Say we have xi is, for example, 1. Yeah. And then, for example, we set a value of h, for example, 1 as well. Yeah. So then to approximate the gradient at 1, yeah, the gradient at 1, it means that we will insert the value. Say I will take the forward scheme. Yeah. If we take the forward scheme, so that means that we will need the value of fxi plus 1, yeah, minus fxi divided by the distance, yeah, between xi plus 1 to xi, which is 1. Yeah. So here, if we want to find the derivatives at point 1 using forward scheme, so that means we can insert the value at the point forward, which is f2, yeah, because we use the increment of h, so that's 1 plus 1 is 2, minus f1 over h is 1. So that if we want to solve this one and we want to find the gradient at 1, so what we can do is just insert the value of 2 here. So insert the value of 2 here in x value, so that we have the function, the value of the function at 2. Yeah, so that we have the value of the function at 2. We just find the value here. And we insert the value at 1 as well. We put this value 1. Yeah. So that we have the function value at 1. So that we have f1. So then we insert this into the equation. So we get the first derivative already. Yeah. So as easy as that. Yeah. So we just find the value, inserting the value at this point. Yeah. So that we can calculate the gradient.
Oh, all right, ma'am. So this numerical differentiation is used to find the gradient.
Yes. Yeah, correct. Yeah. Yeah, differentiation. Yeah, first derivatives means the gradient. Yeah, first derivatives means the gradient. Okay. Any other question? Okay, so that now we will continue. We have discussed about finding the first derivatives. Now we can extend it forward, finding the second derivatives. Yeah. Turunan kedua. So that if we remember the second derivatives, if we imagine a curve, for example, if we have quadratic curve, so that will be the maximum or the minimum points, yeah, of the curve. So that we can also to find this one using numerical methods. So how to find the second derivatives? So that again we will use the Taylor series expansion, but because second derivatives will involve more points, so that we will expand further backward to I minus 2. Yeah, to I minus 2. So that now we expand the Taylor series not only one step behind backward, but 2 steps behind. So if we have point I, and then we have I minus 1, now we expand it to I minus 2. So here. So that if we use I minus 2, so that the value, the function value at I minus 2, that can be approximated by fxi plus xi minus 2 minus xi. Yeah, so that the distance here will be minus 2h. Yeah, so that this will be minus 2h, yeah, times the first derivatives at x at xi plus xi minus 2 minus xi, which is squared over 2 factorial times the second derivatives and so on. So we truncate the rest here, so that the rest here will be at power 3, yeah, to the power of 3, x to the power of 3. So that we substitute this value with minus 2h. So that again, that will cause the sign will be opposite for each term. So that will be positive, negative, positive, yeah. So that should be minus 2h, which is squared. So that will be positive for h, which is squared. Now that divided by 2 factorial, so that 4 divided by 2, that will be 2. So positive 2 squared h times the second derivatives at xi plus the truncated terms. So that we have one term here, we have one equation here. So this is the first equation. And then we need the second equation, which is found by do the expansion forward one step behind. Yeah, so that we have fxi minus 1, which is approximated by fxi minus h, fx and xi, and so on. So we have the second equation here. Now we want to find the second derivatives. Yeah, so if we want to find the second derivatives here, so this is what we want to find. So that if we want to omit that one, yeah, so that we can do subtraction. Yeah, we subtract it. But in order to remove this term, so that means that these equations should be multiplied by 2. Yeah, so that if it's 2, so that will be 2 as well, and that will be 2, and that will be 2. Yeah, so that this one minus that, so that will be omitted. So that we can write it down here, so that will be fxi minus 2 minus 2 times fxi minus 1. So this is the left hand side. Now we go on to the right hand side here. We have fxi minus 2 times fxi. So that will be minus fxi. And then here we have 2 times h squared, the second derivative of xi. Now this one is subtracted by 2 h squared over 2 factorial. So that will be gone. Yeah, so that means 2 squared h minus 1 squared h. So that will be positive 1. So that will be h squared, the second derivative of xi, plus the truncated s at the order of h to the power of 3. So that if we want to find that one, so we move all this term to the left, and then we divide it by h squared. So when we divide it by h squared, it means that this one should be divided by h squared as well. So that will result in h to the power of 1. So that means this will be first order accurate scheme. Yeah. So this is how to find the second derivative. So this is the result. Yeah. Finding the second derivatives, which is using backward scheme. And this will be first order accurate. Yeah, so that will be 1 divided by that one. So this is first order accurate scheme. So this is how to find the second derivative. So if we have that equation before, and we want to find the second derivative, so we can insert this value, yeah, in the equation. So that once we have this value in the equation, so we easily can get the second derivatives for the curve at that point. Yeah. Okay, so this is to find the second derivatives using backward first order scheme. Yeah, first order backward scheme. Okay. So this is the example. Say we have the same result from experiment. Say we want now to find the second derivative at point 2 using backward scheme. So that this will be fx2, which is 5.5, minus 2 times fx1, 2 times 4.1, yeah, positive, plus fx0, which is 2.3, and that divided by squared h. So that we will have the second derivatives directly. Yeah. So without finding the curve, yeah, without finding the trend line, for example, without complex calculations, yeah. So using the data points here, we can get the second derivatives already. And in this scheme, using this formula, we have the first order accurate scheme. Yeah, any question?
I want to ask something, ma'am.
Yes, Adim?
If I see the second equation in the slide 27.
Slide 27.
Yes.
Okay. Yeah.
If I see the second equation here, it's already is it uh, can we find the second derivative through only this equation? Because I think if we know the first derivative of fxi, we already know the second, ma'am, without without omitting the second term, ma'am.
Yeah. If we want to, if for example we have the value of f accent already, yeah, here, yeah, we can find the value of the second derivatives. Yeah. So for example, here we have, say, the first derivative which is taken from here, yeah, for example. So we have this equation. Using the backward or forward scheme, we can find the first derivative so that we insert the equation here. So that will be fine as well. Yeah. But why we do subtraction like this one? Because it's easier to see the resulting order of accuracy from this scheme. Yeah. So because if say you insert this value, yeah, for example, we insert the value of the first derivative from the previous scheme, for example, in which say we can take that from the second order scheme, or we can take that from the first order scheme. Yeah. So that will be mixed around of the resulting level of accuracy of this problem, yeah, of this formula, whether this is first order or second order accurate. Yeah. And so with this, yeah, with this, it can be clearer in terms of defining the level of accuracy for the scheme. Yeah. But if we have the value of f accent, yeah, we can insert that directly. Yeah. So yeah, the final result, yeah, the final result still becomes the first order scheme. Yeah, regardless of what approximation that we use to find the first derivatives, because the resulting here we have will be h to the power of 3 divided by h squared. So the final result will be first order accurate. Yeah, yeah, we can use that if we have the first derivative already.
Oh, okay, ma'am. Thank you very much.
Yeah. All right. So that is to find the second derivatives. Now, we have discussed about first order, second order accurate scheme. Now, we can also get higher order different scheme. Yeah. Increasing it to higher order accurate scheme. Yeah. So for example, here we have seen before the calculation of finding the first derivatives and the second derivatives, in which both are first order accurate scheme. But we can also find, for example, the extension. Yeah, so we can combine the Steller series expansion, in which we can get the first derivative, which is second order accurate scheme using forward. Yeah, forward scheme, finding the first derivative, but now it's second order accurate. So again, with this one means that if we want to increase the order of accuracy, of course, it means that we cannot find the gradient by only connecting a linear line between 2 points. Yeah. So for example, here we want to find the gradient at xi. So that means that this gradient should be approximated with a function which is more complex. So at least it should be a quadratic equation. So that with quadratic equation, it means that we cannot get the quadratic equation only from connecting 2 points. So that it means that we need minimum of 3 points here. So that we see to find the first derivative of xi at higher level of accuracy using forward scheme, it means that we have to include the calculation of the point at I plus 1, I plus 2, and the point I itself. Yeah. So this is to get higher order first derivative, yeah, using the forward scheme. And how to get this equation? Yeah, we can get it by doing subtraction or addition to the Taylor series expansion that we have, such as what we have performed to find the second derivatives. Yeah, so it's similar to this one, yeah, as what we've seen before here. But if we want to find the first derivative to a higher level of accuracy, it means that what we want to omit is not the first derivatives, but we want to omit the second derivatives. Yeah, so that means we have to subtract the second to the first equation, in which it will removing the second derivative terms here. So what we have will be the first derivatives, and the truncated bed will be the order of h to the power of 3. And when we find fx and xi, so that will be divided by h, so that the resulting will be second order accurate scheme. So this is how to combining the Taylor series expansion, so that we will have a formula that give us higher order accurate scheme. Yeah, and also we can use the central difference scheme or central scheme, in which what we have discussed before, we can find the first derivatives by connecting the points after and before of that point itself. And this will result in second order accurate scheme. We can also find it, we can also find the second derivative from this scheme. Yeah. So this is find second derivatives. Now it also has second order accurate scheme. So that if we look at in general, yeah, so that it means, say we want to find the derivatives, we can use the backward approach, in which we use the points before to calculate the derivatives, or we can also use the forward approach, in which we use the subsequent points, yeah, the points after, to calculate the derivatives. Or we can also use the central scheme, in which we use the adjacent points before and after of the point itself. Yeah, and if, say, we want to extend it to higher order level of accuracy, so that means we will involve more points. Yeah, so if we want to increase to third order, fourth order, it means that we will include more points in the calculation. Now the question is, which one is a better approximation, which is a forward scheme or central scheme or backward scheme, and why? Yeah, and when would you use which? Yeah, so this might be not easy to be answered. Yeah, so say we want to compare two schemes. If these two schemes are different in level of in the order of accuracy, so it's pretty easy to say which one is better. Say, for example, we're comparing the first order with the second order accurate scheme. Of course, we can say that the second order accurate scheme will be better. Yeah. Now the question is, for example, if we have both at the same level of accuracy, for example, we have first order accurate forward scheme and the first order accurate backward scheme, which one is better? Yeah. So this is not easy to be answered, and this is really depends on the problem that we solve. Yeah. Depends on the curve, yeah, on the solution itself. Sometimes backward is a better approximation, yeah, sometimes forward is a better approximation. Okay, so we will now see the problem, the example problem in the book, in which here we have we want to use the forward and backward difference approximation of O H. So this means that the first order accurate scheme, yeah, first order forward and backward scheme, and using a central difference approximation, which is second order accurate scheme, to estimate the first the first derivatives of this function. And this derivative will be analyzed at x equals to 0.5 with a step size of 0.5. And we also asked to repeat the computation using smaller step. Yeah. And we want to compare to the true value, because this is quite a simple equation, so that we can get the true value already. Yeah, we can get the true value directly. So we will compare that. Okay, so we will see the book. Yeah, so this is an example problem 4.4. Okay, so we will look in the book here. Is it shown already? Okay. Yeah. So here we have the example. Yeah. To find the derivative of this equation. So this is incorrect. Yeah, this should be minus plus 1.2 without 5. So you can correct that. And here we want to find the derivatives based on forward scheme, backward scheme, and so on. So here we use first the forward scheme. Yeah. So that if we want to use the forward scheme, so that to calculate fx and xi, so that will be fxi plus 1, yeah, forward points, minus fxi over h. Yeah. So that we see here that the value of fxi plus 1, yeah, which is x is 0.5, with h is 0.5, so that means 1, yeah. So fxi plus 1 is 1, yeah, xi plus 1 is 1, so that we insert the value to the equation, and then we get the value is 0.2. And if we find the value of 0.5, which is fxi, so that will be 0.925. We insert in the equations, and then we get the value will be 0.925. So that the first derivatives using using forward scheme can be calculated by 0.2 minus 0.925 over 0.5, which is this is h. So that we have the result will be minus 1.45. So this gives the error, the relative true error of almost 60%. Yeah, almost 60%. Now we try the second method, which is the backward scheme. Yeah. So with the backward scheme now, so it means that to calculate the gradient now is approximated with the point backward. Yeah. So fxi minus fxi minus 1 divided by h. So we have fxi value will be 0.925. And then fxi minus 1 value, we insert the value at 0, that will be 1.2 divided by h. So now we have the value of this one, and this gives the relative true error of about 40%. So in this case, we can see that the backward difference scheme will give lower error compared to the forward scheme. Yeah. So in this case, with the same level of accuracy, which is first order accurate scheme, both are first order accurate scheme, but we can see here that backward scheme is better compared to the forward scheme. Now we want to use the central difference scheme. With the central difference scheme, now that this can be calculated by the point after and before, so that we have fxi plus 1 minus fxi minus 1, and that divided by the distance, which is 2h. So that if we insert the value of fxi plus 1 and fxi minus 1, and we divide it by 2 times h, so that will be 1. So that this will give an error, the relative true error of almost 10%. So we can see here that this is the best among the three of the scheme that we tested. Yeah. So this is the best, and this is logical because this is second order accurate scheme. Yeah, of course, this will give better accuracy compared to the two other scheme. Okay. Next, we will try the second question, which is we want to repeat the computation using a smaller step size. So now if we want to calculate xi plus 1, now that will be at the position of 0.75 from initially is 1. Yeah. And I minus 1 now becomes at 0.25. Yeah. So that now we insert the value to the calculation. So we see here that now with the forward scheme, still first order accurate scheme, but now using half of the step size, now we end up with the relative true error becomes less than 30%, which is initially is 60%. Yeah, initially 60%, and we half the step size. Now we get the error is also half of the initial error. And now using the backward scheme again, yeah. So we see here now that the error is already also reduced. Initially 40%, now becomes 21%. Now, if we use the central divided difference scheme, which is second order accurate scheme, and using half of the time step, now we got that the error become as low as 2%. So here we have some conclusion, yeah, that we can get from this example is that if we want to compare the schemes which is clearly have different level of accuracy, of course, the higher order scheme will give better approximation. Yeah. And if, for example, we want to reducing the step size also reducing the error. Yeah, reducing the step size also will reduce the error. And that with smaller step size, we can see that the difference between the selection, yeah, which one to choose, whether forward or backward, become less significant. Yeah, become less significant. So we can see here that initially the difference is between 60 to 40%, yeah, with large step size. Now, if we're reducing the step size, the difference now becomes 5%. So less significant difference between which scheme that we should choose. Yeah. So that it become less sensitive to the selection of the scheme as we reducing the step size. So that is the second conclusion. Yeah. And of course, if next here we can see the example of central difference, which is second order accurate. So this is a combination, yeah, between the higher order scheme with a low step size, with a small step size. So this will give the best accuracy. Yeah. So this will minimize the error. Okay. So this is the explanation for example 4.4. All right. Any question?
Excuse me, ma'am.
Yes, Vivi.
For the first derivative, we can get the slope gradient and draw it on the graph. And for the second derivative, what we get, ma'am?
Yeah. Now this is quite difficult, yeah, to illustrate. Yeah. Perhaps first order is easy because we can imagine that will be the slope. Now second order, usually if we know about second order, if we have the quadratic equation, yeah, so that will give the maximum or the minimum point. Yeah, the maximum or the minimum. So still, I think you still remember if we have this graph, yeah, xy. So that will be the minimum, so that the second derivative will be equals to 0. Yeah. So that is the second derivative. Now, what about the third derivative and so on? So yeah, it's not very easy to imagine that. Yeah. But often we need that calculation. Yeah. Often we need that calculation. So graphical representation is not always possible to show the derivatives. Yeah. So yeah, I think that is only answer that I can give.
Okay, thank you, ma'am.
Yeah. Okay. Any other question? Okay, so I will return to the slide. Yeah, I think we understand that already. So you have seen here that nothing is difficult with numerical method. Yeah, we use a very simple procedure to approximate the value. You have to approximate a very complex equation. Okay, now back to what we talked last week, yeah, and earlier about when we talk about approximation, of course, we will have error. And we have discussed two types of error, yeah. So we have talked about random error, which is this relates to the capability of the stored number, yeah, the computer to store the number. And the other is about truncation error. Yeah, truncation error, in which truncation error is relates to the simplification in the Taylor series expansion. Yeah, simplification that we use in the Taylor series expansion. So that if we have a number, approximated value which contains an error, so that here we denote this value with x wave. Yeah, so x wave here is the approximated value of x. So say here x already contains an error, and we do the operation, arithmetic operation forward, in the calculation, because we can imagine that numerical method with dealing with lots of calculation, so that when we have a value, we will carry on that value forward in the subsequent calculation. So here, for example, we have addition. Yeah. So say we want to add two values which already contains error. So for example, we have u wave and v wave, both contain error already. So that what is the estimated error of the addition of these two values? So that will be the error from the value in u plus the error in the value of v. So that we have an error propagation. So it's accumulated over and over, and it's increasing and increasing. Yeah. And if we do subtraction, for example, we subtract the value of u, which already contains an error, to another value, which also contains an error, so that the resulting error is not the subtraction, but it's an addition as well. Yeah, so that means that the error will increasing. Again, if you do multiplication of two values which already contains error, so that the resulting error will be the error in one value v multiplied by the magnitude of the value u plus the error in u, which is multiplied by the magnitude value of v. Yeah. So we see that if you have large value of magnitude here, so that it will be multiplied lots with the magnitude of the value itself, so that the error will be propagated. And also if we do division, so that this is the estimated error. Yeah. So that we can imagine here that with more calculation needed, yeah, it means that the error will increasing and increasing. So that dealing with this, dealing with error, particularly when we talk about round-off error and truncation error, yeah, so that if we do the calculation, so this relates to the stability of the calculation. Yeah, we have a term here which is called the condition number. So if you ever learned about matrix before in calculus, yeah, so perhaps you still remember that a matrix will have a condition number. So we can calculate the condition number of a matrix. So a condition number for a matrix is actually a measure of whether the system is well conditioned or the system is ill conditioned. Well conditioned means that when we have a problem, and then that problem can be easily solved. Yeah, so we can get the solution very easy. So that is a well conditioned problem. Now, ill conditioned problem is a problem which is difficult to get the solution. For example, if we perform numerical method, if we perform the calculation on it, so that it's very difficult to get the final solution, because it's quite sensitive to the changes of the value. Yeah, so that this is dealing with the stability of the calculation. So that what is actually the condition number here? So the condition number is the value, the approximated value times the gradient of the approximate value divided by the function itself. So this is actually the measure of the conditions to which x is amplified by x wave. So it means that, for example, if this value changes a lot, yeah, with one of the variable here is changed, so that means it's very ill condition, yeah. And if the condition number is approximately 1, so this is called well condition. If the condition number is larger than 1, so this is called ill condition. So ill condition problem means that the problem is not easy to be solved, and it will have usually stability problem, yeah, during the calculation, because it's very sensitive to round of error. Yeah, so this is dealing with round of error. So round of error is actually a small change of value, yeah, because we do rounding, but in fact it will change the value of the solution very significant. Yeah, small value of x changes, but the value of, for example, the function value or the derivatives changes a lot. So this means that this is in ill condition. So again, if you look at the error analysis, we have two types of error. And as what we've seen before, that the truncation error is dealing with the truncated terms that we don't use in the calculation because we simplify it. Yeah. So that we know that the truncation error will be the order of h, or the order of the step size. Yeah. While the round of error, yeah, the round of error here is dealing with the capability of the computer or the machine. So this is called the machine epsilon. So that if we see the machine epsilon itself, yeah, so the machine epsilon here is actually an invert of h, yeah, an invert of h. So what does that mean? It means that when we use larger step size, yeah, larger step size, so means this will be divided by a large value. It means that the round of error will decreasing. Yeah. Why? Because if we use large sum step, it means that we reduce the arithmetic operation needed, and therefore the chances of the propagation of the round of error can be minimized. Yeah. So we see here that in one case here in truncation error is related to h. So if h is larger, it means that the truncation error is larger. While on the other hand, if we have h is larger, the round of error will be minimized. So that the total error will be the addition of, or the summation of the truncation error and the round of error. So that you see here, truncation error decreases as h decreases. So if you use smaller time step, yeah, smaller step size, it means that the error reduces, as what we've seen in example problem 4.4. But on the other hand, if we talk about the round of error, if we decrease in h, it means that the round of error increasing, because it means that we will need more calculation in order to get the complete solution. Yeah, so that here, so this is the illustration, yeah, for the total error. So the truncation error will increasing with increasing step size. Yeah, larger step size means that the truncation error increasing. On the other hand, larger step size means that the round of error decreasing because less computation is needed. Less arithmetic operation is needed. So that the total error will be the addition of both. So that here we can see that there will be a point of diminishing returns, or this will be the optimum selection for the step size here. So at this point, the error will be minimized. Yeah. So it means that the selection of the step size here should be chosen in which that it will minimize the total error. Okay, any questions?
Excuse me, ma'am.
Yeah, Sultan?
I want to ask about how can we get the epsilon, ma'am?
Yeah. Yeah. So how to get the machine epsilon here? Yeah, this depends on the machine. Yeah. This is a nice question. We will check in the book whether it has an explanation on that. Yeah, so this epsilon, yeah, this depends on the capability of the computer to store the number. Yeah. Okay, so we see here in the book. Yeah, so yeah, so we have, say we have a value, yeah, in which if we have the approximated value, so that we will have an error, yeah, dealing with round of error here, yes, in which here we see the explanation, yeah, yeah, in which because we're using the rounded value here, of course we have the error associated with the round of error. So that here with the round of error here, so that has an upper bound of epsilon. Yeah, so this epsilon is the limit, yeah, the limit of the value that can be stored by the computer. So that will be the upper bound. Yeah, so say we have the maximum possible value of difference of ei plus 1 minus ei will be 2 epsilon. Yeah, so that is 2 ei minus 1, ei plus 1 minus ei will be 2 times epsilon. Yeah, so if we look at here, so that will be epsilon will be the upper bound, the upper limit. Yeah. So we can see the maximum difference of the value. Yeah. Maximum difference of a value. So this depends on how many bits, yeah, the computer of, how many bits the computer, and the exponent as well. Yeah. So I think this depends on the exponent as well for the upper bound. So, and that will be 2 epsilon is the upper bound, because the upper and the lower bound, so that will be 2 times, yeah, because it has the lower and the upper, so that will be 2 epsilon. Yeah. Okay, so I think this is dealing with the capability, yeah, of the computer to store the number. Previously we have the calculation, the capability for storing number up to exponential to 10 to the power of 38 and 10 to the power of minus 38. Yeah. So yeah, I think it relates to that. Yeah. But here is not defined as well in the book. Yeah. Of how finding the epsilon. Okay, so this one, okay, we have the example here. Yeah, so we can see here at 4.8. MATLAB, yeah, in this example, has a precision of about 15 to 16 base 10 digits. Yeah, it means that it will be 10 to the power of minus maximum of minus 16. Yeah. So that a rough estimate will be about this order. Yeah. So that will be 10 to the power of minus 16. Yeah. So that we insert this value here. Yeah. So approximately this the epsilon value. Yeah. So for MATLAB, it means that in this case, MATLAB is only 16 and has a precision up to 16 base. Yeah, 16 base 10 digits, only up to here. Yeah, this is for MATLAB itself. Yeah. Actually, we have 32 bits computer. So this can be up to 10 to the power of minus 38. Yeah, but perhaps there is some limitation for MATLAB. Yeah, so it said here that the precision for MATLAB is about this value. Yeah, so I think that is how to get the epsilon. Yeah, so it depends on the machine and also depends on the software as well. Yeah. Okay, so is that answering your question, Sultan?
Yes, ma'am. It's clear. Thank you. Thank you.
Yeah, and this is also relates to why it's, as I said before, yeah, why is it important to choose whether to use single precision machine, single precision or double precision? Yeah, so if you do complex simulation, yeah, you will have to choose this one because this will affect the value of the epsilon here. Yeah, I'm not sure what is the exactly value of the epsilon here for each of the software. Yeah, but at least for 64 bits is can be up to this value. Now, whether the software can handle up to that accuracy, yeah, for the rounding to storing the number, now that depends on the software itself. But the machine at the moment can up to this value, yeah, the minimum and the maximum from minus up to positive, yeah. Okay. So that is about the epsilon, yeah. And we will return to the slide. All right, so that will be the end of part 4, yeah. And we still have time, so that I will continue on the next discussion, which is about the roots of equations. So this will be included in the second part in the book. Okay, so part 2 is about roots of equations, and when we talk about roots, yeah, so roots is akar-akar, yeah, akar-akar persamaan. So we have known this in calculus before, and this is easy to get, yeah, if we have quadratic equations. So you can find directly the roots of the equations. Now, we will do the same, in which the objective is to find or to solve for the x value so that fx will be equals to 0. Yeah, so if we remember what is the roots of an equation, yeah, so say we have this graph, yeah, so that the roots will be the one that intersect with the x-axis here, yeah, with intersect with the axis. So that this value means that this is fx equals to 0. So any value in which the value of fx will be equals to 0. So this means the first root, and this one is the second root. Or equivalently, we want to solve for x such that, say we have gx, a function which is equal to another function. Yeah. So we have a function which is equal to another function, so that we want to solve for which x which satisfies this equation. Yeah. On the other hand, we can also move that to the left side, say like that one, so that we have gx minus hx, that will be equal to 0. Yeah, because this moved to the left, so that will be equal to 0. Or we can say that gx minus hx here becomes a new function which is called fx. So if fx will equals to 0, so that means that the solution here will automatically satisfy this equation. Yeah. Okay, so we will see the explanation here. One of the example here, say we have this one. Yeah. So this is the example in the book from chapter 8. We have a mechanical engineering problem here in which we want to find the value of K, which is the stiffness of the vibration system, such that the displacement of xt becomes 0 at t equals to 0.5 seconds. So what we want is to have the displacement is equal to 0 when the time is known at 0.5. So that we have time here is known as 0.5 second. This one as well, and that one as well is known. Now, the initial displacement is x0, so this is the initial displacement, and the initial velocity is 0. Yeah, and the mass m and the damping, the mass, the damping, which is c, the damping factor, and lambda here is already known. Yeah. Now the question is to find the value of k. Yeah. So this is the problem, is to find k value. So how to find k value? Of course, we need to find mu first here, yeah, from this equation. So that means that we want to have that equals to 0. Yeah, so this equation will be equal to 0, and we have to find mu. Yeah, and once we have mu, so that we can calculate the value of k. Yeah, because k is our goal. Now, how to get this value? This is not easy because we have mu, which is here, and we have mu, which is inside the function of cosinus and sinus. So how to get the value of mu, which will satisfy this equation equals to 0? So this is called the root. Yeah. If we have the function which is equals to 0, so the solution for that will be the root. So this is not easy to be solved by using what we have learned before if we have quadratic equation, yeah, like that, and so on, over 2a. So this is not, we cannot use that equation. All right. So this is what we have learned before. When we have a quadratic equation, the problem is, what if we want to solve the previous equation? What if we want to solve, for example, fifth order equation here? Yeah, we have x to the power of 5 and so on. How to find for x? Which one is the root? Or for example, we have sinus x plus x equals to 0. What is the value of x? Which will be the root for this equation? So this is not easy to obtain from calculus. Yeah. So that what we can do here is that we can use a non-computer method, which is closed form solution. Yeah, so this is based on analytical, and also graphical solution, which is sometimes often inaccurate. Yeah. So this is very relative to what we see, yeah, for example, for graphical solution, and the measurement is not always correct. Now, when we talk about numerical methods, so this is suitable. Yeah, we can use the help of computer to get the solution. So there are many ways, many methods, yeah, to approximate the roots of equation in numerical method. Now, what we are going to discuss in this chapter will be about bracketing methods. Yeah, and next week we will talk about the open methods. Yeah, so bracketing methods, it means bracketing, it means putting a bracket or giving a limit. Yeah, so bracketing, giving a limit, in which we have two methods, which is included in the bracketing method, which is called the bisection method and false position method. Okay, and also we will have open methods. So we have several examples, several methods for open method, and also roots of polynomial. Now for this course, we will focus only on bracketing and open method, in which here in bracketing method, we will focus on bisection method and false position method. And for the open method, we will talk about Norton-Raphson and second method. Okay, so that we will see the first one using graphical is how to get the graphical solution is just to plot the function. So you insert a value of x and get a value of fx. So you draw points there and you plot the function here. So that when you get the function, so that you can approximate the value here. Yeah, what is the value of x in which fx will be equals to 0. So this is the graphical solution. So the root axis, whenever there is a curve, yeah, where is a fx which crosses the x-axis. Okay, so we will go back on the parachutist example. Yeah. Say we have this equation, analytical solution before, in which here say we want to find the friction coefficient, or say we want to find the drag coefficient before. Yeah, we said C here is drag coefficient, which is necessary for a parachutist of a mass. So the mass is known, M, and the speed, to have a speed of 40 meters per second at 10 seconds. So that we have mass, we have the gravitational force. This one is already known, and t is 10 seconds, and we want to have the speed of 40. So that the result here will be 40, and that one is 10 seconds. So we have here 40 will be equals to a function of c. So that if we reorganize, we move 40 to the right-hand side here, so that we will have 0 equals to this function minus 40. Or we can say that fc, that will be equals to gm over c times 1 minus e to the power of minus c over mt minus v, and that will be equals to 0. Yeah. So a solution for this will make sure that c, yeah, the value of c will give a value, the velocity of 40 meters per second at 10 seconds. So this is what we want to solve. Yeah. So that we plot gm and so on, this function in here. So this is a function of c. We plot that, yeah, as a function of c. So we insert the value of c from 4 up to 20 here. And then we get the value here for the function. We got the intersection with the x-axis here will be here, yeah, and we just find it the value here. So this is approximately, say this is 12, and this is the half of it will be 14. So that will be 14 point something, yeah, nearly 15. So this is the graphical solution. So based on this, here we got the solution will be 14.75. So this is the result in which this will give with drag coefficient of this value. We can insert that, which we can recheck. Yeah, put this value here, and then we will get the velocity will be about 40. So this is correct. Yeah, so the result will be 40.06, or approximately equals to 40 meters per second. Yeah. So this is the graphical solution in which we we plot the graph. Yeah, we plot the graph, and then we find the value that will intersect with an x-axis. Now, this is not practical if we have complex problem as well, and sometimes it's difficult to plot to find for the exact point here. So that now we will talk about the numerical method to solve this one. Yeah. So first we use the bracketing method. Yeah. And today we will talk about bisection first. Yeah. Bracketing is also called as a closed method. Yeah, closed method. Okay, so before we talk about that, we will see how the roots located in a function. Yeah. Say we have this sort of a function. Yeah. So that say we have a bracket, a limit. Yeah. So we bracket it. We give bracket the lower bracket here, which is XL, and the upper bracket, which is XU. Yeah. So here, say we have two roots inside the bracket. Yeah. So here we have two roots. So that say we have the value of XL and we find the function value of XL, which is positive here. Yeah. So say we have XL. So we find the value of XL, which is positive at this point. And we insert the value of the upper bracket, which is XU. Yeah. And the function value is also positive here. So if we have the function value which are both positive, it means that there can be no root inside the bracket, or there are even number of roots. There can be 2 or 4 or 6, yeah, even number of root, or there will be no root at all. For example, I have a curve which is like that. Yeah, so if I have a curve which is like that, so that if we give a bracket of lower and upper limit of the bracket, so that we have both positive value. So it means there is no root. Yeah, so the possibility, if we have 2 positive value for the roots, 2 positive function value for the bracket, so it means there is no, the chances are there are no roots, or even there are even number of roots. Now the next example on the right, say we have 2 value as a bracket. We have the lower value and the upper value, and we find the function value first is positive, the other is negative, for example. So it means that there should be a root inside. There should be a root inside, minimum 1 root, yeah, minimum 1 root, or odd number of root, yeah, because it's positive and negative. Of course, the curve will intersect with the x-axis. So if we have 1 positive and 1 negative value, it means that we have odd number of root, either 1, 3, 5, and so on. So this is the basis that we use in the bracketing method. So what we do is that we make 2 initial guesses of the bracket, which is a value of XL and XU. So these are required to bracket the root, yeah, so that we check the value of the function at these 2 position. Then if the value of fxl times fxu is lower than 0, it means that, for example, it's negative, it means that 1 positive, 1 negative, or 1 negative, 1 positive, it means that the result will be negative. Yeah, it means that there is 1 root. Yeah, we assume there is 1 root in between the bracket that we give. Yeah. It means that with fxl times fxu lower than 0, it means that the function changes sign on opposite sides of the root. So this is the illustration. For example, we have both positive. So in this case, we have no root. B, we have 1 negative for the lower, 1 value positive for the upper. Here we have 1 root. C, KC, here we have positive and positive. We have 2 roots in between the bracket. Figure G, we have 1 positive and 1 negative. Here, the example, we can have 3 roots in between the brackets. Now, we have other cases in which this is not the general trend. Yeah. For example, here we have a case which is slightly different. Say we have a positive and negative value here for the bracket, but we have double root in which this is maximum or minimum point. Yeah. So here we have a double root. And also, for example, we have one bracket is negative, one bracket is positive, the other bracket is positive. But here we have discontinuous curve. So in this case, it's not easy to define how many roots that's available there. In this case, we have, for example, 2 roots only. Yeah. And figure C, for example, here we have the case of positive and positive. We have sign the same sign, but here we have multiple root. Yeah, multiple root because we have, for example, here we have sort of inflection point there. So yeah, there are some cases in which this is not always true, but in general, we can say that if we have a value which is one positive and negative, at least we have one root inside. Yeah, so that is the basis that used in this method. Yeah, although it's not always. Yeah, although it's not always, but in this case, we assume that if we have an opposite sign for the brackets, so it means that we have at least one root in between. So this is how it works. Yeah. So the first method, which is bisection method. So we give an initial value for the lower and upper bracket. We can take any value there. And then we find for the value for the function value at those points. We find the value of fxl and fxu. If one positive, one negative, or the multiplication is negative, it means that there is one root in between the brackets so that we can continue with the next step. Yeah. And how to find for the root? So the root is simply the midpoint between the lower and the upper bracket that we give. Yeah, so that here the root will be at the middle point between the lower and upper bracket that we give. So this will be the value of the root. And then we find the function of the new root. And if we have the function of the new root, now we multiply it with the value of the lower bracket. If this is greater than 0, it means if it's greater than 0, it means positive. That means that the value will be the same between the lower and the root. So it means that if the sign is the same, it means that there is no root between the 2 points. Yeah, between those 2 points. Yeah. Because this means that it will be the same position. Yeah, so it's not crossing the x-axis. So it's greater than 0. So that means that we have to change. Yeah, because this is greater than 0. It means this is at the same sign. So it means that there is no root. So that the root will lies into the second half. Yeah, so the root is not lying here, but instead it's lying on the second half. So that because it's lying on the second half, so that the next step is to change the position of the lower limit now, so that the lower limit now is the new root. So the new root now becomes the lower limit. So that becomes the new fxl, and that the upper limit remains the same. So this is the new one. So this is the first calculation, the first iteration, and then next we proceed to the next step, updating the limit, yeah, the bracket, updating the bracket so that we move the lower limit now here, yeah. And if we have this new lower limit, so that now we can predict the new root. So the new root will be at the middle between these 2 points. Yeah, so that will be the new root xr. And then we find the function value of fxr, and then we multiply it with fxl. If it's positive, it means that the root is not lying in between the lower limit and r. Instead, it's on the second half. But because here we have xl, fxl is negative and fxr is positive, which means that the multiplication will be negative. It means that the root is in between the lower limit and the root. So that if this is the case, so that we updating the upper limit now becomes the new root. Yeah, so the upper limit now is changing to the new root and so on. So it will be closer, getting closer and closer to the solution, which is the root of the equation. So this is the procedure, yeah, for the procedure for the bisection method. So basically, very simple procedure, but we do repetition and we check for the error. Is it getting closer to one solution? If it's converged, so that will be the final solution. Okay, so that this is the method generally if x is real and continuous in the interval of lower limit and upper limit that we give as a bracket, so that whenever fxl and fxu multiplied by fxu lower than 0, so we assume that there is at least one real root between the lower and the upper limit. So that means that our bracketing assumption is correct, so that we can continue with the next calculation. And in the interval at which the function changes sign, it means that in this region there is a root, so that we can find the new root by finding the midpoint between this sub-interval. And this process is repeated to obtain the refined estimates. Okay, so we see here step 1, choosing the value of xl and xu so that the multiplication of fxl and fxu is negative or lower than 0. If it's negative, so we can use that initial value as a bracket, so that now we calculate the root estimate here, which is at the midpoint. Once we have this value, so then we multiply it with the value of fxl, so this should be fxl, yeah, l. We multiply it. If the result is negative, so that means there's one positive and one negative. So this is correct, means that the root lies in between this interval. Yeah. So that we find the new root, which is at the midpoint here. Say this is the midpoint. And then that will be the new fxl. Yeah. The new xl. So this is r first, xr. Yeah. The new root. And then we multiply it again with the value on the left, yeah. So because this is positive and positive, so that means the result is positive. It means that the root is not lying on the first half, instead is lying on the second half here. So that we updating, this one will be the xl and this one will be xu. Which one? This one should be xu first, yeah. So this one is updated xu, and afterward this one will remain xu. Yeah. So we do several iteration. Yeah. Okay. So this is the first step. Yeah. The upper limit, the lower limit. So this will be okay. So I will erase this one to make this clear. Okay, we will try again this with this one. Yeah, so we have the lower limit and the upper limit. So that will be fxl, fxu. So that will be negative. So the root is in between here. Yeah, at the midpoint. So this is the value. Once we have the value, we can find the value for fxl for the first iteration. With this one, we multiply with fxl and it's negative. It means that it lies in the first half here. Yeah, so because it's lying on the first half here, so that now we find the midpoint here. This becomes the new root. So this is the root for the second iteration. So it's denoted with xr2. So that we find the value of fxr2. We multiply it with fxl. It's both positive. It means that the root is not lying there. So that the root will be on the second half here. So that because it's lying on the second half, so it means that now the lower limit should be updated into the new root. So this will becomes the lower limit and the upper limit remains the same. And then we find the midpoint here. So that will be xr, the new xr for the third iteration So it will be here. And then we find again the function value here. And we multiply by fxl if it's changing value. So it means that the root lies in the first half here, and so on until we get up to the result, which is close to the actual result. Yeah. So the value of fx will close to 0. Yeah. Or if we do iteration, so that we can repeat the iteration up to when the relative error becomes very small. Yeah, the approximate error becomes very small. So this is how the criteria to stop. Yeah, when we can stop depends on what we want to calculate. If we have the true solution, so that we can calculate the true relative error here. So which is the value of x true minus x approximate over the x true value times 100%. If we don't have the true value, so that we can calculate the approximate relative error, in which the value of the new calculation or new iterations minus the value of the older, the previous iteration over the value of the current iteration, that multiplied by 100%. Now, because the value of xr here can be calculated back with xu and xl, so that for specifically, yeah, only for bisection method, so the approximate error can be calculated by xu minus xl over xu plus xl times 100%. So that with this one, we can get the approximate error and when to stop when the approximate error becomes lower than the prescribed error. So we can get any value here. We can put any value, depends on our need, how many accurates, how much accurate we want. For example, 0.1%. So when it's below 0.1% difference, so then it will stop. Okay, so we will see the case of parachute is here. We have this function, yeah, and then we put 40 into the function, move that to the right, so that we have fc here should be equal to 0, and that will be the solution. So this is how it goes with the bisection method. First, we assume a bracket value, yeah, we assume 2 bracketing value. And now we assume it to be 12 and 16. Yeah, we assume 12 and 16. So we insert into the equation. So we get when 12 here. So the value of fx is positive 6. And the value at 16 here is negative 2. And we check whether this is already positive and negative because it's correct. The multiplication is lower than 0. It means that there is a root in between the bracket that we give. What if, for example, we give 2 brackets, for example, I take 11 and 13, and both 11 and 13 here is positive value. It means that there will be no root in between, and we have to choose for other bracket. Yeah. So if we came across the value in which we give for the initial value for the bracket is not positive and negative, it means that we have to choose another value for the bracket. Okay, so this is already correct, so positive and negative, so that there's a root in between those values. So that now we calculate the root for the first iteration is 8 at the midpoint, so that is the average between xl and xu, so that will be 14. And the value at 14 here, we see the value is positive 1.569. So that when we multiply it with the lower limit, it's both positive, yeah. So the result will be positive. So it means that there will be no root in between 12 to 14, but the root will lies in the second half, which is 14 to 16. Yeah. So that now we use this one, 14, as the lower limit. The upper limit remains the same. Now setting this value as the new limit, now we can calculate for the new root. So that for the new root is the midpoint between 14 and 16. So that now we have the new root is 15. Now we find the function value at 15. Now we have minus. So this is positive and negative, which means that the root will lies into the first half of this region, yeah, or of this interval. So that because it's here, so that now we update the upper limit. Now become the new root becomes the new upper limit, while the lower limits remains the same as the previous iteration. Okay, so we have that one. So that when we proceed with the calculation, yeah, this is the first iteration, the second, the third, and here we have up to 6 iteration. We end up with the root, yeah, which is 14.813. And we have the approximate error is already very low, which is 0.42%. And the true error here is if we have the true value, yeah. So the true error will be 0.291. Okay, so we see here that we get the solution in 6 iterations with the error already low. Okay, so this is about the bisection method, and we can see the flow chart here for the bisection method, so that if you want to, for example, construct this code in Python or Fortran or other language, yeah, programming language, so that we start here and we input the value of the lower and upper limit and the criterion to stop, yeah, the error, the relative error to stop, and the number of maximum iteration if it's needed. And the first step is to check whether our bracket, the bracket that we give, is already containing the root in between. Yeah, so we check for the value fxl times fxu, whether it's lower than 0. If it's true, then we can proceed with the calculation. If it's not, so then we have to return and get another value for the bracket. Okay, so that once we have this already correct, we have one root in between, so that we can find the new root here. Yeah. So this is to check the criteria to check whether we want to repeat the calculation or not. Now the main thing is here to find the new root, which is the average, yeah, the midpoint between the upper and the lower limit. Yeah. Once we have that, so then we can calculate for the error. After the error, then we test whether for the next calculation, whether the root will be located on the first half or on the second half of the interval, and so on. And then we repeat the calculation. Okay, so this is about bisection method, and what is the advantage? The advantage is it is simple and estimate a maximum error of this one. Yes, so this is a maximum error, and it's guaranteed to be converged. Yeah, so the convergence is guaranteed. The downside is that it's quite slow. Yeah, because we always find the new root, which is always half of the interval. Yeah, so it's quite slow. And another problem is to find two good initial estimates which define the bracket. Yeah. So of course this sometimes cannot be too easy to get the bracket. Yeah. So that when we have this case, we can use, for example, the help of graph. For example, we draw the graph, and then we know the approximate position of the root. Or we can also do incremental search or doing some trial and error. So this is about bisection method. And yeah, here, say we want to find the absolute magnitude of error up to 10 to the power of -4. So that will require about 15 iteration to get to the accurate solution. Yeah, 15 iteration. Yeah, so this is quite slow. Yeah, this is quite slow. But yeah, the convergence is guaranteed. Yeah, the convergence is guaranteed. It means that as long as that we can give brackets, yeah, in which there is a root in between the brackets, so that the convergence will be guaranteed. It means that we always have a solution. Okay, so I think that is for today. Any questions for bracketing method?
Excuse me, ma'am. I want to ask something.
Yes.
To set the value that where we stop to iterating, it's up to ourselves or any other way to set it, ma'am?
Yeah, so this depends on us. Yeah. If you have a problem from the book, it will be given from the book. Yeah, it will be given by the book. Or for example, in the midterm exam, so I will set the value up to which level of error we want to get the result. Yeah, but in real problem, sometimes we don't have that limit. Yeah, so that we have to prescribe it by ourselves. We have to set a value. Yeah, and that's really depends on the case. Yeah, on the level of accuracy that we want. Yeah. So it's relative, yeah. It's relative to us, yeah. Okay.
Okay, thank you very much, ma'am.
Yeah. Okay. Any other question? Yeah, I hope this is clear enough for the bracketing method, and yeah, we will continue to the other. This is bisection method, yeah, bisection. So that bisection, this method is called bisection because it's divided into two sections. Yeah, bi means two. Section is area. Yeah, section or yeah. We divided the interval into two sections. Use slightly different approach. Yeah, slightly different approach to find the root. Okay. So yeah, I think that is for today. Any other question? Okay, if there is no questions, so I will close this class. Thank you and wassalamualaikum warahmatullahi wabarakatuh.